We have seen that when we multiply an applied force by the time of application of that force, we are talking about impulse, Ft. And we've seen that applying an impulse to something changes its momentum. Impulse produces a change in momentum. Now we want to discuss something similar. Multiplying the force on something by the distance moved by that force. The quantity force times distance is called work. To calculate the work on something, force and distance moved must be in the same direction. For example, when you lift a barbell, you push upward and it moves a vertical distance upward. Force and distance moved are in the same direction. So we say you do work on the barbell. The amount of work equals the force it takes to lift it multiplied by the distance it is raised. According to the equation W equals Fd, if you lift twice the load the same distance, you do twice as much work on the barbell. Or if you lift twice the load twice the distance, that's 2 twices, you do 4 times the work on the barbell. The work done becomes energy acquired by the barbell. More generally, the work done on anything changes the energy of that thing. Energy is a concept that has intrigued investigators for a long time. Its definition isn't as clear-cut as the definitions for concepts such as force, acceleration, and momentum, because energy comes in different forms. For the time being, we can define energy as the ability to do work. The energy acquired by the raised barbell has the ability to do work on things if it falls. It can transfer its energy elsewhere. Ultimately, that energy may spread to atoms and molecules and increase their speeds. Energy is something that can be transferred or, as we will see, transformed. Consider the work done when a block of ice is pushed up a ramp. For simplicity, we'll assume no friction between the block and the ramp. Our guy pushes with a force F, a distance d, and gets the block to the top. We'll assume the weight of the block is 400 newtons. But since it's a ramp, our guy doesn't have to push that hard on the block. He finds a force of 200 newtons does the job. So he pushes the block a distance of 6 meters to the top of the ramp. Then the work he does on the block is 200 newtons times 6 meters equals 1,200 joules. The unit of energy is the joule, where 1 joule is the work done by 1 newton over a distance of 1 meter. So at the top of the 3-meter high ramp, the block of ice has acquired 1,200 joules of energy that it didn't have at the bottom of the ramp. Here's an interesting fact. Suppose the same block were lifted vertically to the same location. Then the work done in lifting it is the full weight of the block multiplied by the 3-meter height. That's 400 newtons times 3 meters, which equals, get this, the same 1,200 joules. So the 1,200 joules of energy acquired by the block is the same as the work done to slide it up the ramp, or the work done to simply lift it 3 meters vertically. The 1,200 joules of energy depends only on its change in elevation, the height to which it's raised. We call this acquired energy gravitational potential energy. We define it as weight times height. If we express weight as mg and height as distance h, we say potential energy equals mgh. The potential energy mgh is really an energy difference. It is measured relative to a reference level. For example, if the potential energy of the block atop the ramp is 1,200 joules, then its potential energy is 0 joules at the bottom of the ramp. We find that potential energy, or we shall see, any form of energy, has significance only when it changes. When it does work, it transforms to energy of some other form. For example, if the ice slides back down the ramp or falls off the edge, its potential energy will transform to energy of motion. We'll cover energy of motion in our next screencast. But before that, I want to leave you with a question. If our block of ice weighed 500 newtons instead of 400 newtons, how much force would the little guy on the ramp have to exert to slide it up the ramp at constant speed? Until next time, good energy.